Okay, folks, let's get started. It's 10 o'clock. So, well, first of all, welcome back. This is the course called Computer Aided Engineering, and very incorrectly, what some people refer to as CATIA class. This is not CATIA class. You're supposed to know CATIA, okay? We use CATIA to solve certain engineering problems, okay? Now, notice that I better stay here because I want my sound to be recorded too. Down below, it says this can be the recording of the material delivered to the earlier class, 8:30, or the 10 o'clock class. I tried to record it at 8:30, but there were some technical issues. So this is going to be recorded, and it's going to be posted on YouTube. So when the people from Group 1, 8:30 class see it, they might say, well, wait a minute, this was not what he told us. He was saying something else. Other things, but that's because it can be from either one of these two sections. Now, I got an email from a student on Friday saying that he has contracted COVID and he's going to miss the Monday and Wednesday lecture, or Tuesday and Thursday lecture. The lab may be okay, or no. I told him, don't worry, because everything that I do in class is going to be posted. Okay, now it becomes your responsibility to go and watch it. Okay, so same thing with the lab. The labs, the first hour, 15 minutes, I make a presentation. It's going to get recorded and posted. We'll come to those in a minute. So I would like to discuss the syllabus first. The syllabus has been posted on Blackboard for the past 2 weeks. Okay, and it was updated last night. Okay, so it's pretty much the same thing with some very, very, very minor changes, which I will discuss it in a minute. Okay, so obviously there is information about myself, and if you have any questions, the best way is to email me, and I'll return your that much I can guarantee. Return it within 24 hours, maybe within an hour or so. But if you ask a question which meant that either you were not here, which is fine, or you did not watch the recording, I will not give you an answer. I will refer you back to the recording, go watch it. How do I do this? How do I do that? Well, go watch it. Okay, because either I discussed it, you were not here, or it's recorded and posted and you didn't bother looking at it. So those questions, I will refer you to the video unless there's something you got a point. Okay. Now, at this point, I have no clue how many GAs I've got. It looks like they're telling me you have 8 GAs, and these are the people. Okay. With the exception of one of them that has been moved out to a different section, these people all took this course maybe 2-3 years ago before COVID, and maybe even before that. They're graduate students. They know what's going on. They've taken the course. They know CATIA, so they're fairly reliable. Okay. Once I know how many of these people I've got, then I will put the information here and let you know. Okay. Now, we are using 2 textbooks. These are my own. I've been using them for the last 15 years, 16 years. It's up to you. I don't care. If you can borrow it, copy it, I don't know, download it, I have nothing to do with it. We'll come to that in a minute. The bookstore has placed order for 7 of them. I don't know. So there is a midterm, first midterm in 6 weeks, June 17th. That is the day before the summer break, during the lab, which means that don't make any arrangements, any plans, or if you're making plans, they better be legitimate, okay? And that has to be assessed by myself and the associate dean if needed, okay? Things happen, I understand that, and we will accommodate you. For example, if you have, hypothetically, if you have on Friday, you have your sister's wedding, brother's wedding, I don't know. Yeah, as long as you can prove that, that's easy to do, okay? We'll accommodate you somehow, okay? Or if you get sick, obviously, that's our job, we have to do that. But anyway, so under normal circumstances, don't leave town because it's the day before the weekend. before the summer break. There's going to be a midterm there, okay? And it's during the lab, as I pointed out. Let me see. Oh, can I use my own computer? We don't care during the lab, but on the test, you have to use the installation that's on the in room CEI 2105. You have to use that computer, because if you use your own, we cannot open it, then that's your problem. Okay. So during the lab and aside from writing the test, no problem. Do whatever you want. The course syllabus on a day-by-day basis is here. There may be some changes, rearrangements, something may be left out, something may be added. I'll tell you, okay? But that's what it is, okay? The yellow stuff is before the midterm. After the midterm, if you want, burn your book, burn your notes, because the subject is going to completely change, and it's not going to cover the stuff that you already did. And the final exam is not cumulative, okay? There's your midterm. Oh yeah, lab 6, yeah, that's good. These are important things that you can read. It has to do with accreditation. As far as the breakdown of the marks is concerned, 10 assignments. Remember, there are 12 labs. One of them is for midterm, so that leaves you 11 labs. One of them you can miss if you want, or if you got half a mark in one lab because you didn't do your, minimum. Let's put it that way. And you came to the extra lab, that 0.5 is going to get changed to 1. There's no problem. And at the end of the day, 10%, if you can breathe and you can be in the lab to show your work to the GA, you should be guaranteed of that 10%. Okay? So I better watch what he's saying, because these are being recorded and put on YouTube also, so it's not good. Okay, the test, the way these labs work is that I make a 50-minute presentation, 50-minute, 1 hour, sometimes maybe 40 minutes. I make my own share. And then let's hypothetically say at 9:30, we give you an assignment. An assignment is a couple of problems. And we ask you to do certain things. Maybe do problem 1, maybe do problem 2, maybe do both, something like that. And the GA, once you're done at 10:30, not earlier than that. So 1 hour, we give you time to do something on it. You're supposed to do the work. Raise your hand. The GA is going to come and check your work. As long as there are no fundamental issues, if you are completely off track, of course, he or she is going to say, you can't do that. Do it again. You still have another hour to go. So during the last hour, you can check your work, okay? And as I said, if you have put a reasonable effort into it, that doesn't necessarily have to be all right, okay? Then you get a check mark and you can go home. So basically, I'm saying that if you want that 1 point that day, you have to show up between 9:30 and 10:30. Now, I don't want to say that, but if you borrowed your friend's USB and showed that to the GA, okay, well, there's no way for us to know, but they'll cause yourself a problem on the test. We'll come to that in a minute, okay? Now, the tests are open book, open notes, no internet access, no cell phones, obviously, and material cannot be shared. So if you want to copy your friend's notes, do it ahead of time. You cannot borrow his or her notes during the test. The other thing I'm going to tell you is that on the test, there's 71 people in this section. You're going to be sitting next to each other, okay, in the computer room. You have 2.5 hours, something like that, 2.5, 3 hours. They're in the lab, okay? Wait a minute, I'm going to say something important. Wait, what the hell was I going to tell you? Oh, yeah, but you're going to sit next to each other, 70 people next to each other. I'll try to spread you out a bit. But even if you're sitting all next to each other, the 2 people next to one another do not have the same test, okay? So you better concentrate on your own test and don't waste time. Okay? The test, we'll discuss it later on, but there could be 4 problems to do and a bunch of questions. Okay, so this is why it's important for you to not only be able to do things on the computer and get nice colors, but have some basic understanding of what you're doing. And those are going to be in the form of short questions, etc. So, all right, so any questions here? Okay. There's something, as I said, if you miss the lab, unless it's a valid reason, a documented valid reason, we are not going to accommodate you. I mean, basically, there's no makeup. I mean, she's around 1 point. But even if you have a legitimate reason, it's okay. We'll accommodate you somehow. The 1 point, we're going to somehow accommodate you. Maybe ask you to do a different problem, something like that. Now, if the midterm is missed for a valid reason, and things happen, the weight is going to be transferred to the final exam. Okay, so there is no makeup. It's very legitimate, but even if it is legitimate, it's going to be transferred to the final exam. Okay. Now, yeah. Okay. So that's. Please make sure you read these things. Right. There is something called supplemental privileges. Probably some of you know. If your grade is such and such, GPA grade. Gross GPA is such and such, and you have failed one course, the academic standing committee reviews your stuff. I think it's going to be sometime in October, and if they want to, they can give you a supplemental exam for one test, one exam, one course. There is supplemental privileges available in this course. Some courses don't have it because those that required, for example, technical communication and design and things like that, you can't go back and do it. But for this course, there is. We will give you the opportunity to basically redeem yourself, but that test is not going to be until December. Okay, if you're given supplemental privileges, then you can write it next week. It's going to be in December, unless you're in Germany working for Scheffler or some co-op in BC. I don't know, something like that. Then I have to see how we can accommodate you for that supplement. You don't have to come back here in December and write it. Okay, yeah, there's really not much in this course syllabus. Yeah, so let me go to the other document that also was posted. Where is it? Okay, just bear with me for a second. Where is the other one? This one. This also was posted for the past 2 weeks. And there's a couple of items that I want to bring to your attention. We already talked about most of the stuff that I wanted to, but yeah, if there are any issues with your midterm, unless it's a last minute, of course, that we'll look at it later on, but you know that there's going to be a wedding, sister's wedding, brother's wedding, whatever, that you have to go do it, please, in the next 2 weeks, okay? If you already have something, you know it now, and it's legitimate, reasonable request, you have to talk to me in the first 2 weeks. If you have letters of accommodation, first 2 weeks, okay? I will contact those people who were allowed special accommodation, quiet space, and things like that. I will send them an email saying that you better do it in the next 2 weeks, because I don't want the day before the test, somebody shows up and say, I need special accommodation. I had the letter, because you're responsible for submitting those letters in the first 2 weeks of the course. Okay, good. All right, now, everything is going to be recorded. This is stuff from last year, okay? I don't guarantee that everything was recorded and posted, including the midterm and the homework and the final, after the final was written, of course. But for example, if you go here, let me see, control, if you go to this guy, this is lecture playlist. Let's see. The sound is not going to come out.
When I was a student, I'd write long essays that I'd work on for days. But now I'm writing short emails.
That's me in my basement recording my first lecture.
4 o'clock.
Okay.
Welcome to the computer engineering course.
Here
this is probably more
close, but not identical.
And assuming that they have. Okay, let's move on.
Some problems.
Let's do that.
Yeah. Okay.
Will be recorded.
So you have many.
Is there a way you guys can check
Professor,
that?
it's recording.
Many options. stuff from last year, stuff from 3 years ago, 4 years ago. Now, those were not your course that were recorded. There were other courses that I did some of these problems in them, but it's a mishmash of different places in the channel. Okay. Okay. What did I want to say? I think I said something. Any questions? No questions. Very good. Okay. So let's go down to business, this real stuff. So we already did this. Now we're going to do chapter 2 of the book. Okay. Now, for you guys, I have an extra 5 minutes. Good for you, probably, because I ran into some issues in the first lab. So they're responsible for that stuff also. I'll let them know. So let's say we have a part like that. You see that over there? Part like that. It says the bottom of it is clamped. It's made out of steel. The bottom of it is clamped. And the top is subjected to a load like you see over there. This is the kind of problem that you did in Dr. Green's class, stress analysis. I doubted that you did it in deformable bodies, but in stress analysis, you did something called energy methods and solved one specific problem which should look like that, because it can be done analytically. Now, we're going to do it for this week. We're not going to do it with those little lines that you draw and you say the cross-section is circle and the I is this and A is that, etc. We want to pretend that this is actually a solid part like that, and the load is applied and the bottom is clamped. First of all, it's very easy to generate good-looking garbage in this course. Good-looking, colorful, all the numbers. There's no guarantee that those numbers are right. And that is not the purpose of this course. The purpose of this course is to show you how it's done. Are the numbers right? They may not be, because your mesh is not fine enough. Because maybe, I'll tell you in just a second, here it says the bottom is clamped. Well, what does that mean? What do you mean clamped? When you did Dr. Green's class for deformable body, you drew a line. And you said, this point is clamped. Point clamped, there's no ambiguity. But the bottom of this thing is clamped means that, okay, this part is actually made, now you have to clamp it. So either you go and spot weld around that edge, or seam weld around that edge, or get an adhesive, put it underneath that face and stick it there somehow. So these are all different. Okay. For the case of this course, because we don't want you to make decisions like that, we'll tell you, it says bottom face, I'm telling you, bottom face is clamped. In other words, everything on that face does not go anywhere. Okay? All right, so now if you do it some other way, if this part is the real part and it's actually spot welded, obviously the stuff that you're going to get is not going to match your colors, your numbers necessarily. But spot welds, seam welds, adhesive, close to that area, you have a problem because there's a lot of ambiguity. But you go far away, it makes no difference. And the effect dies away very quickly. But in that area, if your job was a welder, that's where you're interested. Don't care about what happens in that top left corner. But if you want to use this thing as a component in a car, for example, or a bracket, then it becomes important also what happens up there. Okay? Yeah, the face is loaded. What do you mean? How do you load the face? Well, did I put a rope around that and pull that 2,000 pounds? Did I attach a hook at the end and put a cable or rope there and pull the cable with that hook at the end? So these are all ambiguous. These are all assumptions that in real life yet you have to make. This is why you should never do stuff like this without actually seeing the part. You have to see the part, at least to have an idea how this is loaded. But we can't do that in this course. We're going to tell you the face is loaded. Okay, so don't put the force on the edge. Put it on the face, and you see how to do it. Okay, material properties are given here. These are properties of steel. you can input these numbers, and I show you how to do it. But those are the least of our concern, because there's a material database in CATIA. It says steel, go get it. Okay, unless we specifically, we will tell you, I don't want the stuff in the CATIA database. I want 30 million PSI. You should know how to do that. Okay, I mean, may ask you to do that. Not a lot of points, maybe out of 20 points, maybe 1 mark, just so that we know where to do it. But anyway, the whole idea of finite element is to take finite element. You break your part into little pieces, little elements. Yeah. And in this case, the ones that you're going to be concerned about in this course are either 4-noded elements on the left or 10-noded element on the right, linear, parabolic. Those are more accurate. Those are less accurate. But since accuracy is not our issue in this course, okay, I mean, I don't know, we don't care unless we specifically tell you to do something. You're on your own, you decide, and you're not going to lose marks on that. Now, the thing is that every of those black dots is a node. It's called a node. So the one on the left has 4 nodes. The one on the right has 10 nodes. At each node, we have 3 unknowns, 3 translations. So when you think about it, that element on the right, there are 30 unknowns in it. Okay, if you wanted to do that manually, for one element, you have to write a 30 by 30 matrix and do something with it. I mean, imagine there's thousands of these, hundreds of thousands of these. So it's practically it's not possible. But anyway, degrees of freedom, you know what it means, the unknowns associated with each node. For these solid elements, 3 translation. Good question to ask on the test as one of those things. Now, look, obviously you might say, I wrote it down, or I have the copy of the book, or I printed something from the screen. No problem. But these take time for you to go. I mean, I'm just letting you know. These take time to do those questions in half an hour and then go and do the rest of the stuff. Anyway, move on. Now, so why are we doing this? Well, at each node, you're going to find the displacement. Software is going to find the displacement. Once you find the displacement, you can find the strains. Go back to stuff that you did in Dr. Green's class. Once you find the strain, you can find the stresses if you have material properties. So at each point, you have 6 unknown stresses right up there. 3 normal and 3 shear stresses. So now what? Okay, I found it. How do I use it? What do I use it for? Well, you're tempted to say that, oh, if the stress is big, then the part is going to fail, or the part is going to plastically deform, which means essentially fail. When you take your screen door and deform it so that it doesn't go back to where it was, that's fail. You have to go by another one, basically. Okay, so big stress, that's a bad answer. Stresses can be very large, still, no problem. For example, you take a piece of a submarine, a little piece of that hull. Take it to the bottom of the ocean. There's a gigantic stress there, in all directions, hydrostatic pressure, huge. But you bring it out, it goes back to, it compresses it down below. But you bring it out, it goes back to the original shape. So hydrostatic stress, regardless of how large it is, has no impact on failure. These are things that you did in stress analysis course. So what they did, they said, okay, let me take these 6 components of stress, lump it together, and I get something called von Mises stress. Right there, effective stress, that's first one. Effective stress in that weird fashion. If that number is bigger than the yield strength, you have a problem. If that number is less than yield strength, you're safe. I mean, obviously, you need factor of safety and things like that I have down there, okay? So this is how it is used. Now, if you wonder what's the difference between the top one and the middle one, it's exactly the top one, except that's written in principal direction. Principal direction, shears are 0. Look, they're the same. If the shears are 0, these 3 numbers are 0, you get exactly the same von Mises stress. Now, A way that it was described to you also, that graph should be familiar to you, figure on the right side should be familiar to you. So if you assume that you have a plane stress condition, then you can draw the places where sigma von Mises equal to yield strength. You get an ellipse. As long as you're inside of that ellipse, the part was not fail, plastic. Okay? If you're on it, chances of yielding bad. Don't go outside. You can't go outside because the material will yield. Okay. But there's another criteria. That's called von Mises criteria, distortion energy theory, something like that. But there's another one called. Does anybody remember what this? Has anybody seen this graph? This figure? Okay, this is based on Tresca criteria. Tresca criteria says, hey, look, at a point, go find the maximum, at the point, instead of putting all those 6 numbers into that expression, find the maximum shear stress. You can do that. Based on more circle or whatever, you can do that. If the maximum shear stress is less than yield strength, you're safe. Otherwise, it fails. So this is another failure criteria. It's called Tresca criteria or maximum shear stress criteria. And if you put this inside of that, it looks like this. Tresca is more conservative. Notice that if something is safe for Tresca, it is automatically safe for von Mises. But if the material is safe for von Mises, it may be trapped between those two curves. And then it will fail. That's why Tresca is more conservative. That means heavier, more money, blah, blah, blah. But, you may not need that. Okay. Now, you might say, well, Dr. Green showed us how to do these problems with beams. And you're going to do that next week with beams. Well, why should I do this horrible-looking three-dimensional object, etc.? Hey, try to do this thing with that horrible-looking elements. Thousands of I-beams, etc. There's no way you can solve this with those solid elements. So structural engineers, the first thing that they do is they model it as a bunch of beams, lines, frames, and things like that. And then get some information, so has displacement at the joints where an I-beam is welded to another. You get the forces there, okay, a displacement there, and then out of that you can go and look at an I-beam as a unit and break it out one particular I-beam, and then look at the stresses and things like that based on the information that comes from the frame model. Okay. Anyway, so that's good. Okay, any questions? All right, so we're going to do this problem. Okay. All right, so Katia. When you start Katia, by default, the way the system is set up, you can change these things. It gives you a product part. Okay. Products are a bunch of parts together. Okay, assemblies basically, and we're going to do those. We're going to do assembly problems later on, several parts interacting with it. But for now, the first 4 weeks of the course, the first 3 weeks of the course, is going to be single parts. So that being the case, I already killed that product screen. Okay, I'm going to start the part. So it's a good idea to give these proper names. For example, my part in lecture 1. Because later on when you write a test, and there is an assembly of 4 parts, part 1, part 2, part 3, part 4, it's going to be tough to decide who is what. Okay, but here it's okay, I'll call it part 1. But the first thing that I'm going to do, I'm going to save this, because I don't want in 10 minutes or 5 minutes my system to crash, and I haven't saved anything. It's all gone. So let me save this part in a folder that I can recognize. So, and the way I strongly suggest, go and review the stuff that you did in, this is all, these days, you don't have to review it. Just go type save in YouTube, save Katia YouTube, and it tells you these things, okay? You don't need me or Dr. Pushka to tell you that. There is a thing that I created. You're going to save as, folder, desktop, desktop. I make a new folder. I will call it group 2. How about that? Because when you write a test, you're going to have to upload your parts. In this case, one part and one analysis file. If you have an assembly, you have to create all the parts in an assembly. And the product, all the parts are one product or other products if there are any, and analysis. So you got to put the stuff in a place that you can find out where they are. You don't want to look around and see where it went actually by document. I don't know where it went by document. So group 1 there. So that part and the analysis that I'm going to create in just a minute is going to go into that folder. Okay. Say okay, of course. So yeah, good. Let's make it. So on this horizontal plane, I'm going to make a sketch. Oh, by the way, I've changed my units. If you don't remember how to change your units, watch my video from last year, or come and see me, or go on YouTube. Setting the units in CATIA. They'll tell you. Okay, so I'll change it so that it's inches and PSI and things like that. So sketch a circle. It does not have to be here at the center, but I will put it at the center. And the radius of that, I think it was 1. It says radius 1. In that drawing, it says radius 1. So I'm going to dimension this, radius 1 inch. Good. Exit. Now, this thing, where did that go? Looked like that. If I pad, it goes straight up. So that's not going to do me any good. So I want it to go along some kind of a curve, okay? CATIA has a name for that. Does anybody remember what that name is? Yep. Okay, that's good. Keep that in mind. Anybody else? Rip. Because software to software, these names vary. It could be in SolidWorks, they call it sweep. Yeah. CATIA calls it a rip. So you should be aware of these issues here. So let's go and rib it. But the thing is that I need the path here, the path to rip along. Okay. So I'm gonna select this vertical line. Doesn't matter which one you take, and sketch on it that path, that spine. Some probably I don't know, SolidWorks may call it spine, or here they call it center curve. You know, these are all different. Okay, well, not this. There. Okay. So let me make that. Something like this. Let's dimension it. I think the dimensions in that problem, and I'll talk about dimensions in just a minute again, one more time, although I did probably say something about it. This was 8. Okay, and then here to here is 5. 5. Okay. And this thing is 1. Let me say a few words about dimensions. If we gave you a problem like this on a test, and we told you that these are the dimensions. The problem has 20 marks. These are the dimensions. And you either did not pay attention to that, or, okay, you waited until the last minute, and it was too hard to read the stuff and do the work, you just decided, oh, this is going to be 4, 5, radius is 4. You're not going to lose that much mark. Let's hypothetically say 1 out of 20. Everything else right, 1 out of 20. Because either you can't read, or you don't want to read, or you put yourself in that position. Okay? Time was running out. Okay, you have to pay a little bit to be fair to the other people. But not much. So if you left this thing as 1, don't worry about it on the test. Don't worry about it a little bit here in the labs and things like that. Not that much. Sometimes I go ahead and make my own dimension. Now, unless it's a critical issue. What do I mean by critical issue? If you make the fillet radius 5, it's not going to do it for you. Then you put yourself in that position. But if instead of 1, you use 1.3, okay, 0.7, okay, it was just careless, that's all. So in critical things, you have to worry about it because it's just not going to do it. You're not going to be able to finish the problem. That's simple as that. I'll make it one. Let me dimension it. Excellent. Exit. Remember, I don't want to accidentally the power to go, save it. Just click on the floppy. It'll update whatever you saved in that folder. Good. Oh, now we have to do the rib. There's the rib. There's the pad. There's the rib. Let me cancel that for a second. Cancel that because I want to show you something. Okay, so I have two sketches here, right? I have two sketches here. Sketch one was that circle. Sketch two was this thing. Okay, so let me rib it. Let me rib it. And notice that this is orange. I didn't mean it, but accidentally I selected that sketch ahead of time because I was, rushing through this. When I try to rib it, and then some people panic, they don't bother reading, or they read, they don't understand what it says, etc. What it's saying is that, look, that curve that you want to rib, that thing that is my circle, must be a closed curve. But because this was active, when I did the ribbing, it thinks that I want to rib this thing, this L. I don't want to do that, it was just an accident. So if you can control yourself, don't panic. Okay, just cancel it. Cancel it. No. Cancel it. Make sure that this is not selected. Okay, if it's not selected, now rib it. And it says the profile. The profile is that curve. It thought that the profile was that L, inverted L. And the center curve or the spine, which is either sketch 2 or you can do it from the screen, and it goes like that, and it's all saved. All right. Now, the rest of the problem is we have to apply material to this thing, because without applying material, you don't know how the response of the bar is going to be. Aluminum, rubber, steel. So I have to apply the material on it. And apply material is this icon, apply material, metal, steel on that part, and okay. If we insisted that the material have Young's modulus of 0.3 or 30 million psi, then you better change. You better make sure this is 30 million, because you don't know it came out of the database. Double click on it, select the analysis tab, and this is the default value in Katia. 29 million, actually 29 million and 10,000, something like that. If we insist that you make it 30, okay, then change that to 30. It's accepted. You can change it, 30. I'm going to leave it the way it is, okay? And Poisson ratio does not have unit. You already know that. Density we don't need because we're doing a static problem. We will be doing a static problem. And yield strength, totally useless. Totally useless. Katia does not do yielding. It does not model plasticity and things like that. So what is this doing there? Well, they want some genetic number. This is some kind of steel. Yield strength of steel depends on the heat treatment of the steel. The yield strength of a submarine hull is different from the yield strength of an I-beam that you use in this building. For the submarine hull, it could be 10 times more, 10 times bigger. And let me give you this very good piece of advice that somebody gave me 30 years ago. I was always getting confused with this yield strength. I was okay with the Young's modulus, that E of Young's modulus. The guy told me that, look, if you know the Young's modulus, you're talking about metal, we talk about metal. If you know the Young's modulus, just knock out 3 zeros, and it puts you in the ballpark figure. Ballpark. So 30 million, knock out 3 zeros, you get 30,000 psi. Go back to the slide that you're familiar with. 200 gigapascal. Young's modulus for steel, structural steel, is roughly 200 gigapascal. 200. So what is the yield strength in that's not. Knock out 3 zeros. What do you get? Remember, knock out 3 zeros. It's going to be 2. It's going to be 200 instead of 10 to the 9. It's 10 to the 6. It's 200 megapascal instead of 200 giga. Giga is 9 exponent 9. Take away 3. It's 200 10 to the 6. 200 megapascal. Anyway, it's just there for people to look at. We're going to keep it like this. I'm going to save this again. All I have to do is the floppy. All I have to do, I don't have to go to file save manager unless I want to change the name and things like that. What is this? This is what I did, right? Oh, printer? I don't know what I did. It's okay. I think I click on something else. Now, from this point on, you're going to go to generative structure analysis. When it comes to doing FEA in no. What time do you start? We start at 10. Yeah, 10 minutes. Okay. When it comes to doing FEA, you have there's 2 workbenches you can go to. One is called generative structure analysis, right up there. And at the end of the day, you should always go there because that's the only place where you can apply the loads and restraints and things like that. But for meshing purposes, there is something called advanced meshing tool right here, down here. Advanced meshing tool. So if you want a fancy mesh, if you're designing an instrument panel, you need fancy mesh, okay? But for Mickey Mouse problems that you're doing, you can kind of do everything in this course, 99% of the stuff in this course, by just doing it back mesh, generative structure analysis. Okay, so we go there, generative structure analysis. All the screen changes, the interface changes. You don't recognize any of these except for the utility icons down here. And the first thing it tells you is that do you want to do static analysis or dynamic analysis? Okay. I said apply 200 pounds, 2,000 pounds to that face. The bottom is going to be flat. Apply 2,000 pounds to that face. Is this going to be static or dynamic? Static? Okay, let me ask you this. Here's my piece. There's my piece. No, actually, I want to apply 2,000 pounds like that, so that it kind of turns. What is it initially that I'm applying? Initially? 0, right? There's no force. There's no force. I have to build up to 2,000. So no force. Push, 2,000 pounds. It's going to turn around and go. Okay. Slowly push it. Static. Not time independent, because the place that you apply 500, it depends on time. You're applying this force as a function of kind of time. What's the static problem? But if I took a hammer and hit it, or I took this finger, poor finger, which is slowly applying the force, do it right away. It's as if I hit it with a hammer. It becomes a dynamic problem. Okay? So the duration of the application of the load tells you whether it is static or dynamic. In this problem, I want a slowly applied load, and therefore I pretend that it's a static problem. Static, default. Say okay. Okay, notice what happened here. First of all, let me change the rendering here so that this color, when you put material on it, it looks like that. That's fine. I changed the rendering so that it looks. So it took that part, Katia, using a stupid rule, broke it down into elements. That size element. And the rule, I say stupid because I'm just bad way of saying it. it probably says, take the biggest dimension of this part and take a thousandth of it and use that. Okay, that's just based on the dimension of the size. It may not be good for you, so you may decide that I want a smaller one. No problem. So notice that under here is a nodal elements. This is the one that it created. You can change that if you double click on it here or on the screen with the screen thingy. So size is 0.563. Let me make this thing 0.25. There's also this thing about sag. We'll talk about it later. Let's not worry about it. Just watch that green thingy, that green element. I chose linear and I chose 0.25. A lot smaller. If you want to see the mesh, you put the cursor on nodes and elements right there. Nodes and elements. Right click, mesh visualization. There is your mesh. Okay, so if you want to go beyond this, you have to get rid of this guy that's staring at you. This is not the part. You can only apply loads and restraints on the part. This is the mesh. I don't want it to be in front of me because there's nothing I can do. There's several ways of doing this thing. One way is to put the cursor here. I just delete it. The problem with deleting is if you come back tomorrow and you wanted to do the problem, there is no mesh there. You deleted it, okay? But actually the mesh is there, but it doesn't display it for you. You have to say, show it to me again. But anyway, deactivate it. I shouldn't say just gone. The mesh is gone, but deactivate it. Right there. Now I can apply my restraint and the load. So this restraint right here, see that? This is familiar to you? The anchor, what do you call this? You call it clamp, right? Okay, there we are. Don't worry about these things later on. Clamp, it says what is the support? Now this is where you have to decide, should I take the bottom or should I take the edge or even both? I mean, taking both is dumb, but anyway, this is one face, okay? Because when you take the face, it'll take automatically the edge for you. Okay. Now, here's the clamp that was created for you. You can always see it in the tree. Restraint is the clamp. If you want to make changes, you can click on this or click on that. It doesn't matter. And then the load. Check the loads toolbar right there. There we are. First one is pressure. This one says distributed force. Don't worry, we're going to do these. We have 5 more weeks to go, 6 more weeks to go. We'll do it. The second one says distributed force. On what? On that face. On that face. With the first group, I did a little bit of change. With the first group, I'll do it with your tool, but I put in the Y direction. That's not what I want. I want it in, look at this coordinate system. I want it in the X direction. So let me get the Y out. Put it in the direction of minus 1,000. No, not 1,000. 2,000, right? Minus 2,000. There we are. That's better. You can always make changes by double clicking on that or there. Minus because the coordinate system shows you. It really doesn't matter in this problem. Even plus will give you the same response. Okay, good. Now, this is it for this problem. Very simple problem. So first thing, safe. Because if the system goes down right now, my part is safe, but not this guy, not the analysis. A separate file, file is created called analysis file. You better save that because if the system goes and you haven't saved it, whatever you did is going to be lost till next. Not the part. So you go to File, Save Management. Here's the analysis. You may want to give a different name if there's several of these you're going to do for different loading conditions and things like that. But for me, it's okay. You just do one. And I'll just save as. Same name. You can always change the name, etc. and say OK. Save it here and say OK. So now if the system goes, this stuff I already have. OK. And we can run it. The running is done in this icon, which can see makes it look like a calculator. Okay, and in fact, it says compute. You click on it. Yeah. You click on it and say all. We're almost done here. We will say yes. These numbers are totally useless. They give you some idea, and those ideas are not right. Okay, how long it's going to take CPU time, how much disk space you're going to have, disk space and stuff like that may be okay, but that CPU time, unless that number is very large. If you see that, for example, 2e to the 5 seconds, it's going to take a long time to do. But these are Mickey Mouse problems. Just okay, if you want to see the deflection, just the shape, there we are, under images, there we are. You can animate it. And we usually do that to make sure that the first, we didn't forget anything critical, okay? If this guy was going up through, he said, there's a problem with your load somewhere, probably, go fix it. So this is okay. If you want numbers, you go to say displacement, give me numbers. You click on it, and there we are. And if you look closely, you see that at each of those nodes, you have a displacement, 3 components. Remember 3 degrees of freedom? There you are. But I don't want to see it like that. I want a contour. So you can click on the screen on that contour, say, show me average ISO, and change the rendering. There we are. Red means that anything in the red region deflects between 0.0356 inches and 0.359 inches. Okay? Yes. Did you used to get this? Just see that on the images. The one on the left is deflection. The one on the right is displacement. The one in the middle is 1 meter stress. Remember, you have 6 weeks to get here. And the whole purpose of this, and it's a bad idea to try to, just write the cell. These are going to be posted. Watch it. There's no way you can follow me like that, just to see what's going on in the class. Here's the 1 meter stress. Now, a couple of comments here. If let's hypothetically say that this top horizontal piece was very long compared to the base, and you apply the load there, where would you expect this thing to fail? Use your common sense. Where? Very long. You apply a force there. Yep. The curve. But if this was fat and short, not necessarily fat, but it was short compared to the height, then right there. So that's why you have 2 kind of critical areas here, and that which one actually will cause static failure depends on the relative length of these things. Now, but there's two other items that I want to tell you. One is this looks like patchy. I don't like that. Maybe my mesh is not good, and that is true. My mesh is not good. So let me do the first thing. Use, instead of linear, parabolic elements. So we go here. Instead of linear, which I insisted on changing it because I did it with the first group, I changed it to parabolic and run it. More accurate. That's what it is. More accurate. It takes longer. Not for these problems. And after I show you this, there is one last item that I want to do. I'm going to take about maybe 2-3 minutes. What is that thing that I created? These are the things that I created. These are the 3 graphs that I showed you. I want to see 1 meter stress again. Activate. All that patchy stuff is gone. That's the first indication of that mesh that you took initially. There's something wrong with it. Okay? None of these are reliable. None of these. We'll talk about that later on. Last thing for today. Suppose this load was actually applied to the face perpendicular to the face. Instead of making it bend, no problem. I'll go and change the direction. So I go to the load. Instead of in the Y direction, I take the Y out. Instead of in the X direction, I take it and put it in the Y direction, 2,000 pounds. And you're gonna appreciate this 2-minute conversation. Run it, because how you do on the test depends on the next couple of minutes explanation of what I'm talking about. Let's look at the deflection, for example. or stress. We can look at either way. Okay, and look at the view from the front. View from the front. Come on, front. Ah, there we are. So this time, the force is coming towards you instead of making it go this way, bend. Look, deflection on the left, deflection on the right, they look the same. If you plot the von Mises stress, let me deactivate that. Activate von Mises stress. Huh? Everything looks symmetric. So the biggest part of this course on the midterm, we're going to take every problem, use as many planes of symmetry that are applicable. In other words, you should not have modeled this. You should model only half of it. Number one. Number two, the 2,000 pounds that you put in there should not be 2,000 pounds. What should it be? 1,000. Half of it, 1,000. Is that good enough? No. Out of 20 marks, you probably need another 3 marks. Because that middle plane moves like this in a plane, like a roller. So you have to put roller support on that middle, on that plane that you created. Katia does not call it roller. It calls it surface plane. We're going to do that later on. We're going to do every problem we're responsible for using as many planes as possible. This is it for today. Remember, a big chunk of your mark on the midterm hinges on this business of understanding symmetry. And don't just make half of it because you forgot half of the load, you forgot the surface side. If I put hypothetically 1,000 psi on that space, what would you put on the space? 1,000 psi. 1,000 psi on the entire surface. I'm making half of it. What would I put on this space? No psi. That's already taken area into account. Remember, no one points like this. All right, folks. So let me stop. See you on Thursday.